October 14, 1943, 60 American bombers went down over Schweinfurt in a single afternoon. 600 men, fathers, sons, brothers from Ohio, from Georgia, from Pennsylvania. Gone in the space of 4 hours. The 8th Air Force called it the worst day of the war. 5 months later, March 4th, 1944, 28,000 feet above Berlin, a formation of American heavy bombers, B-17 flying fortresses, pushes deeper into the Reich than any daylight mission has ever gone, and flying alongside them something that by every calculation the Luftwaffe had made should not exist. A single-engine American fighter, escorting bombers over Berlin itself. Reichsmarschall Hermann Göring had spent years making a specific public promise. No Allied fighter, he had declared, would ever be able to escort bombers this far into Germany. The physics wouldn't allow it. The fuel mathematics wouldn't allow it. And yet here they were, P-51 Mustangs. Silver and olive drab, 450 caliber machine guns apiece, turning the previously suicidal daylight bombing campaign into something the Luftwaffe could no longer stop. Göring would later tell his American interrogators in the transcripts of 1945 that when he saw Mustangs over Berlin, he knew the jig was up. But here is what Göring didn't understand. Here is what nobody on the German side understood. Not in March of 1944, not in the years of analysis that followed. The plane that killed his Air Force wasn't built the way it should have been. It had a radiator sticking out of its belly like a blister. An absolute catastrophe for an aerodynamicist. It had the wrong engine for the job it ended up doing. And it had a wing that, according to post-war analysis, could not actually deliver what its designers had promised it would deliver. 3 engineering choices. 3 choices that, by every conventional standard of the 1940s, looked like mistakes. 3 mistakes that together created the single most consequential fighter aircraft of the Second World War. Today we are not looking at kill counts. We are not looking at the romance of the silver airframe. We are doing the forensic audit. We are asking the question the German engineers asked in captured factories in 1945 and could not answer. How did 3 choices that looked like engineering blunders combine to produce an aircraft that outran, outclimbed, and outranged everything the Reich could put in the air? To understand what Göring saw over Berlin that day, we have to go back almost 4 years, to a conversation between 2 men that lasted about 30 seconds, and to a decision that on paper should never have been made. April 1940. France is weeks away from collapse. The German army is pouring through the Ardennes. The Royal Air Force is preparing for what would become the Battle of Britain. And a group of British officials calling themselves the British Purchasing Commission, led by Sir Henry Self, walks into the offices of North American Aviation in Inglewood, California with a specific request. Build us the Curtiss P-40 under license. As fast as you can. Britain needs fighters. The man across the desk from them was James Howard Kindleberger. Everyone called him Dutch. He was the president of North American Aviation. He had built the company from almost nothing into a serious aircraft manufacturer. And he had a chief designer sitting 3 offices away who had been quietly obsessing over fighter design for years. Kindleberger went to that designer and asked him a single question. The designer's name was Edgar Schmude. He was a self-taught German immigrant. He had worked at Fokker's American subsidiary in the late 1920s and at General Aviation before joining North American. He was by temperament exactly the kind of methodical, undramatic engineer that nobody makes movies about. According to Schmude's own later account, preserved in his personal papers, Kindleberger asked him plainly whether they wanted to build P-40s at North American. And Schmude, who had been waiting years for a question like this one, gave an answer that has become part of aviation history. He said they should not build an obsolete airplane, they should build a new one. That was the conversation. That was the moment the Mustang came into existence. Now here is where the story starts to get uncomfortable for anyone who cares about how airplanes are actually made. Because what Schmude was proposing was on its face impossible. The British had said they needed planes immediately. Kindleberger walked back to Sir Henry Self and made a counter-offer that no sensible businessman should have made. He told the British that North American could design a completely new fighter from scratch, build a working prototype, and have it flying in 120 days. 120 days to design, engineer and build a military fighter. For comparison, the Lockheed P-38 Lightning took roughly 2.5 years from concept to first flight. The Republic P-47 Thunderbolt took nearly 3. Kindleberger was offering to do the same work in 4 months. The British, desperate for anything, agreed. The contract was signed in May of 1940. And here is what most accounts get wrong. The airplane did not fly in 120 days. That number has been repeated in books and documentaries for 80 years, and it is not quite what happened. What happened was this. The prototype, designated NS-73X civil registration, NX 19998, was rolled out onto the ramp at Mines Field, the airfield that is today Los Angeles International Airport, exactly 102 days after the contract was signed. It was rolled out with borrowed wheels from an 86 trainer. Its Allison engine had not arrived yet. Somebody in the shop bolted wooden dummy exhaust stacks onto the empty cowling so it would look like a complete airplane for the newspaper photographs. It was an airplane in the way that a movie set is a house, convincing at a distance, not ready to fly. The engine finally arrived weeks later, and on October 26, 1940, 178 days after the contract, the freelance test pilot Vance Breeze climbed into the cockpit and taxied out for the first flight. 5 minutes in the air. Then another 10 minutes later, the same day. The men who had built this thing knew in those first 2 brief flights that they had something strange on their hands. Strange because of what was hanging out of its belly. Because Edgar Schmud, under the pressure of that deadline, had made a decision that every other fighter designer in the world would have told him was wrong. He had placed the aircraft's primary cooling radiator, the heat exchanger that pulls waste heat out of the engine coolant, not under the engine, not in the wing roots, where the Spitfire put it, but in a scoop hanging down from the belly of the fuselage, well behind the cockpit, a scoop that stuck down into the airflow like a growth, a scoop that on every aerodynamicist's calculation should have added so much drag that the airplane would never reach the speeds it needed to reach. There was a documented measurable problem with radiators on high-speed aircraft. Lee Atwood, the vice president of North American Aviation, explained it decades later in an article for Aeroplane magazine published in May of 1999. At full power, Atwood wrote the propeller of a Mustang produced about 1,000 pounds of thrust, and the cooling drag from the radiator was on the order of 400 pounds. Nearly half of every pound of thrust the engine produced was being spent just to keep the engine from melting itself. That was the central problem of every liquid-cooled fighter in 1940. Not how to make the engine powerful, how to cool it without destroying the airplane's performance. Most engineers responded by trying to make the radiator smaller, tucking it out of the airflow, hiding it under wing roots, fairing it into cowlings. Schmued's team did the opposite. They put it in the worst possible place. They made the scoop large. They made it prominent. They hung it deliberately behind the cockpit where everyone could see it. The aviation community, when they got their first good look at the design, were polite about it. The British accepted the aircraft. The first production contract was signed. 320 airframes designated Mustang Mark I by the Royal Air Force. But inside the community of fighter designers, there was a quiet assumption that North American had gambled and lost, that the scoop was going to eat their speed, that the airplane would be pretty on the ground and mediocre in the air. There was one thing the outside world did not know. Schmued and his team had not put the scoop there because they were reckless. They had not put it there because they had run out of time. They had put it there because they had read a paper, a dry mathematical paper, written by a British engineer at the Royal Aircraft Establishment in Farnborough, England, in 1935. We will come back to that paper, because first we need to talk about what happened next. Vance Breeze flew NA-73X again the following week, and the week after that. Different test pilots took the airplane up. The numbers coming back were promising but not yet definitive. The scoop, they said, seemed to work. The airplane was fast. It handled cleanly. And then on November 20th, 1940, the prototype crashed. Paul Balfour was North American's chief test pilot. Experienced, confident, the kind of man who had flown enough airplanes to believe that one prototype was at the end of the day like any other. That belief killed the airplane. According to the account Edgar Schmood preserved in his personal notes, the designer had offered the morning of the flight to walk Balfour through the cockpit procedure. The Mustang had a fuel system unlike any other aircraft Balfour had flown. The main tank fed the engine first. When it ran dry, the pilot had to manually switch to the reserve. There was no automatic feed. There was no warning light. There was only a valve and a pilot, who was supposed to remember to turn it. Schmood offered to explain the sequence. Balfour, according to Schmood's account, declined. One airplane, he said, was like another. Balfour took off from Mines Field that morning, climbed to altitude, ran the airplane through a series of high-speed passes. 12 minutes into the flight, over a stretch of open ground west of Lincoln Boulevard, the Allison engine went quiet. Balfour had never touched the reserve valve. The main tank was empty, and at the altitude he was flying there was no time to work the problem. He came down in a plowed field, wheels up, the nose dug into the soft earth. The airplane, the single existing prototype of what would become the most famous fighter of the war, flipped onto its back. Total flight time on the Mustang program to that point: 3 hours, 20 minutes. The Mustang program could have ended in that plowed field. It did not. The airplane was hauled out, rebuilt, and North American brought in a new chief test pilot, a quiet man named Robert C. Chilton, to take it back into the air. Chilton flew NA-73X for the first time in early 1941. He left a note in his own records, preserved to this day, that has become quietly famous in aviation circles. He said the airplane was clean flying. He said it had no bad vices. A plane every established designer had said should not have been built. Constructed in 102 days. Crashed on its 5th flight by a pilot who thought he knew better than the man who designed it. And now, flying and handling better than any American fighter then in service. The engineers at North America knew something the rest of the aviation world still did not know. They knew why they had put that radiator where they had put it. And to understand what they had gambled on, we have to leave California entirely. We have to cross the Atlantic. We have to go back to 1935, to that research building at Farnborough. The man working there was Frederick Meredith, a British engineer, not famous, not well connected, working a problem the entire aviation community considered a permanent limitation. You designed around cooling drag the way you designed around gravity. It was there. You accepted it. You moved on. Meredith asked a question nobody else seemed to be asking. What if the waste heat did not have to be waste? He published his report in 1935. British Aeronautical Research Council Reports and Memoranda number 1683, titled in the careful academic way of the period cooling of aircraft engines with a special reference to ethylene glycol radiators enclosed in ducts. It was dry. It was mathematical. And what it argued, if you read it carefully, was revolutionary. Meredith said this: if you design the cooling duct correctly, if the air entered through a carefully shaped intake, if it slowed inside a diverging diffuser, if it passed through the radiator matrix under pressure, and if it then exited through a convergent nozzle, the waste heat would do something strange. It would accelerate the exiting air. The hot exhaust stream would leave the duct faster than the cool air had entered it. And in physics, when a mass of air leaves an aircraft faster than it entered, that change in momentum is thrust. The cooling system, in other words, could work like a crude low-temperature ramjet. Not enough thrust to fly the airplane, but enough thrust to cancel out most of the cooling drag, to turn the airplane's biggest performance penalty into something close to zero. The industry, when they read Meredith's paper in 1935, mostly ignored it. Theoretical papers were being published constantly. Most of them elegant on paper, were useless in practice. The Supermarine Spitfire, then in development, incorporated a mild version of the idea, a ducted radiator in the wing root, not designed to wring maximum thrust out of the heat rejection, just to keep the drag manageable. The Messerschmitt Bf-109 later borrowed similar principles. But nobody was betting a fighter's entire performance on the Meredith effect. Nobody, that is, except a small team of engineers in Inglewood, California, who had read the paper carefully and decided to build an airplane around it. Edgar Schmood had read it. Ed Horkey, the young aerodynamicist Shmued had hired straight out of Caltech, had read it. Lee Atwood had read it. The three of them had understood what nobody else in the aviation world had understood. Lee Atwood explained in that 1999 Aeroplane magazine article exactly what his team had committed to. They were going to design the entire rear fuselage of the Mustang around the radiator duct, the intake shape, the diffuser angle, the radiator matrix, the exit nozzle, every dimension calculated to extract the maximum possible thrust recovery from the Meredith effect. The numbers Atwood published were staggering. Against 400 pounds of raw cooling drag, the properly designed duct would produce roughly 350 pounds of thrust. Net cooling drag dropped to 50 pounds, an 85 to 90% reduction in the single biggest drag penalty any liquid-cooled fighter had to pay. Translated into flight performance, that meant the Mustang could do things no other fighter could do with the same engine horsepower. It could cruise farther on less fuel. It could reach higher speeds at the same throttle settings. And this is the part that would matter most. In 1944, it could carry an enormous fuel load over enormous distances, because the airframe was not fighting its own cooling system. North American did not own a transonic wind tunnel. They rented the 10-foot Galsit wind tunnel at the California Institute of Technology and ran their duct designs there. Over and over. Refining the intake, refining the diffuser, refining the exit door. They treated the cooling system not as an afterthought. They treated it as a component of the propulsion system itself. That was the difference. That was what every other designer had missed. Every other designer was still thinking about cooling the way you think about air conditioning in a house. A necessary loss, a cost of doing business. The North American team was thinking about it the way modern jet engineers would think about air handling, as part of the engine, as part of what pushed the airplane forward. And when the Mustang began flying in combat with the Royal Air Force in 1942, first as the Mustang Mark I assigned to tactical reconnaissance and ground attack roles, the pilots started reporting numbers that did not add up. The Allison-powered Mustang at low altitude was faster than the P-40. Same engine, same horsepower, but faster. It was faster than the Spitfire Mark V, which had a better engine. At 20,000 feet, it was about 30 miles per hour faster than the P-40. Same engine. The scoop, the thing every aerodynamicist had looked at and quietly called a mistake, was doing exactly what Meredith's paper had promised it would do. The airframe was in effect being pushed forward by its own waste heat. The Germans, when they eventually captured Mustangs and took them apart, spent significant time studying that duct. They never quite replicated it. Not because they could not have figured out the mathematics. They had brilliant aerodynamicists. But because by the time they understood how important the duct was, they no longer had the industrial capacity to redesign their primary fighters around it. One engineering mistake. One radiator scoop that looked wrong to everyone who saw it. 350 pounds of thrust recovered from what should have been pure drag. But the Mustang was not finished making trouble for itself, because for all the brilliance of the radiator duct, for all the elegance of the airframe, the airplane had an engine problem. And by the spring of 1942, that engine problem was going to nearly kill the program. The Allison V1710 was on paper a competent engine. It was reliable. It was American. It was cheap. It made about 1150 horsepower at low altitude. And it ran cleanly for hundreds of hours between overhauls. And above 15,000 feet it died. Not all at once. What happened above 15,000 feet was that the Allison supercharger, the device that compressed the thin high-altitude air before feeding it into the cylinders, ran out of capability. The Allison had a single-stage supercharger, kept simple in part for export contracts. Above 15,000 feet, it could not compress enough air. Horsepower dropped. Above 20,000 feet, it fell off a cliff. By 25,000 feet, the Allison Mustang was gasping. And that was a catastrophic problem, because the air war over Europe was being fought at 25,000 feet and above. The Luftwaffe's frontline fighters, the Messerschmitt Bf-109 and the Focke-Wulf 190, were optimized for high-altitude combat. American and British bombers were cruising at 25 to 30,000 feet. The Spitfire, Mark IX, powered by a Rolls-Royce Merlin with a two-stage supercharger, worked well at those altitudes. The Mustang, the fastest Allied fighter at low altitude, was useless as a high-altitude interceptor. The Royal Air Force used it for what the Allison was good for: low-level ground attack, tactical reconnaissance, shooting up German trains and trucks in occupied France. Necessary work, dirty work, but not the work the airframe was capable of. By the spring of 1942, there was a real possibility that the Mustang would go into history as a brilliant airframe fitted with the wrong engine. A cautionary tale in a different way than Balfour's crash would have made it a cautionary tale. This one slower, quieter. The story of an aircraft that flew for years, did competent work, and never became what its designers had believed it could be. And then on April 30th, 1942, a 30-minute flight at a Royal Air Force airfield in Cambridgeshire changed everything. The airfield was Duxford. The commanding officer of the Royal Air Force's Air Fighting Development Unit stationed there was Wing Commander Ian Campbell Orde. He had been evaluating Mustang Mark I aircraft for the RAF. He had reached the same conclusion everyone else had reached. Brilliant below 15,000 feet. Useless above it. But Campbell Orde had done something none of the other evaluators had done. He had invited a civilian test pilot. From Rolls-Royce, from the company that made the Merlin engine, to come to Duxford and try the Mustang for himself. The test pilot's name was Ronald Harker, 33 years old, former Royal Air Force pilot, working in 1942 as a senior test pilot at Rolls-Royce's Hucknall flight test establishment. Harker climbed into Mustang Mark I tail number AG422 on the morning of April 30th. He flew it for about 30 minutes. When he landed, he already had the memo written in his head. Harker's assessment documented in his formal report to Rolls-Royce management and preserved in the Hucknall archives was straightforward. The Mustang airframe, he wrote, was among the best he had ever flown. Cleaner than the Spitfire below 15,000 feet. Better handling, better range, better everything that mattered except at the altitudes the war was being fought. What it needed, Harker argued, was the new Rolls-Royce Merlin 61. The same engine that was transforming the Spitfire Mark 9. Put that engine, he wrote, in this airframe, and you would have a fighter without equal at any altitude. That was it. 30 minutes in the cockpit, one memo, and the entire trajectory of the Mustang program changed. The memo went to Rolls-Royce management, then to the British Ministry of Aircraft Production. Then, after sustained lobbying at the highest levels, including from Major Thomas Hitchcock, the American Assistant Military Attaché in London, to the United States Army Air Forces. The British moved first. Rolls-Royce converted 5 Allison Mustang airframes to take the Merlin engine. These became the Mustang X series. Powered by the Merlin 65, an evolved variant of the engine Harker had recommended. Captain R.T. Shepard, Rolls-Royce's chief test pilot, took the first Mustang X into the air on October 13, 1942. The airplane that had been gasping at 25,000 feet was now climbing past 30,000, holding 430 miles per hour of level speed at altitude. The Americans, meanwhile, had been doing the same thing independently. North American Aviation's engineering team had begun converting 2 P-51 airframes to take the Packard-built licensed version of the Merlin, designated the V-1650 Series 3. On November 30th, 1942, Bob Chilton, the same Chilton who had rebuilt the crashed NA-73X, took off from Mansfield in the first XP-51B. He climbed past 30,000 feet, and then the cooling system failed. A chemical reaction between the ethylene glycol coolant and dissimilar metals in the redesigned plumbing had scaled up the radiator matrix. Chilton brought the airplane down, trailing white smoke engine temperatures climbing toward destruction. But before the failure stopped him, before he had to bring the airplane home, Chilton had recorded a level speed of 441 miles per hour at 29,800 feet. More than 100 miles per hour faster than the Allison Mustang at the same altitude. Rate of climb roughly doubled. At every altitude, the United States Army Air Forces did something they had never done before. They ordered 400 Merlin-engined P-51Bs in August of 1942, 3 months before the first XP-51B had even flown, placing an order for an airplane that did not yet exist. on the strength of what a British test pilot had written after 30 minutes in a cockpit. But there was still one more engineering problem to solve. And it was in some ways the most embarrassing of all of them. The original belly scoop, the brilliant Meredith effect duct that had made the Allison Mustang so fast, had a subtle flaw. When Chilton pushed the Merlin Mustang past 400 miles per hour, the airplane began to shake. Not a violent shake, a deep rhythmic rumble. The pilots who flew the early XP-51B could feel it through the seat. Through the stick. The engineers at Enaca took the airplane apart to find out why. What they discovered was that the intake, the mouth of the scoop, had been mounted too close to the underside of the fuselage. At high speed, that intake was ingesting the slow-moving turbulent layer of air that always clings to an aircraft's skin. The boundary layer. Turbulent air entering a duct designed for smooth flow was disrupting everything Meredith had predicted, and the disruption was creating that rumble. The fix documented in the Enaca test reports was almost embarrassingly simple. They moved the scoop down, away from the fuselage, by about 1 inch. That small gap allowed the turbulent boundary layer to slip past the intake rather than be swallowed by it. Clean air entered the duct. The rumble disappeared. The duct's efficiency improved. An inch of empty space. That was what stood between a fighter that shook itself apart at high speed and a fighter that would fly to Berlin. But that fighter, the corrected Merlin-powered boundary layer adjusted P-51B, had one more surprise waiting for it. And this one nobody would discover until after the war. Because the wing that Edgar Schmued had promised the world, the wing that was supposed to be the crown jewel of the entire design, was in a very specific technical sense about to fail at doing the one thing it had been engineered to do. And somehow that failure was going to be the reason the airplane would win the war in the air. The wing that Edgar Schmued had designed for the Mustang was on paper a scientific breakthrough. It was called the NAA/NACA-45-100 airfoil, developed jointly between North American Aviation and the National Advisory Committee for Aeronautics. And what made it revolutionary was a promise. The promise was called laminar flow. Every wing at speed has a layer of air moving across its surface. On a normal wing, that air begins smooth near the leading edge, and then within an inch or two of chord breaks down into a turbulent boundary layer. That turbulence creates drag. On some wings it creates a lot of drag. Schmued and his team had designed a wing whose maximum thickness was pushed back farther from the leading edge than any American fighter wing had ever placed it. In theory, the smooth laminar flow would extend across nearly half the wing's chord before breaking down. In theory, the drag would be dramatically lower than any competing fighter. In theory, because here is what post-war Enaca testing found. The Mustang wing in actual combat service almost never maintained true laminar flow. The surface finish on production aircraft was rough. Rivet heads, panel seams, paint, dust, the occasional bullet crease. Even a fingerprint left on the leading edge during a pre-flight inspection was enough to trip the boundary layer. In practice, the air over a Mustang wing transitioned to turbulent flow far earlier than the theoretical airfoil shape had promised. The wing failed, in a very specific technical sense, at the exact thing its designers had said it would do. And yet, the airfoil shape itself, laminar flow or not, was one of the cleanest high-speed profiles anyone had designed, even with turbulent boundary layers, even with production imperfections. The Mustang wing gave the airplane a tactical Mach number of around 0.78. The Messerschmitt Bf-109 0.75. The Focke-Wulf 190 similar. The P-38 Lightning 0.68. The P-47 Thunderbolt around 0.71. In the thin air above 30,000 feet, where the Luftwaffe had always held the advantage, the Mustang could push harder before the controls went heavy, before the airplane started fighting the pilot, before compressibility took the aircraft away from the man in the cockpit. A wing that failed at its stated purpose, and succeeded at a different purpose entirely. That was the third mistake. That was the third engineering choice that turned out not to be a mistake at all. Just a different answer than the one anyone had been looking for. The corrected P-51B Merlin-powered boundary layer adjusted laminar flow that was not actually laminar began arriving in England in the fall of 1943 On December 1st, 1943, the United States Army Air Force's 354th Fighter Group, freshly trained in California, flew its first combat mission from Boxted Airfield in England. A fighter sweep over France. No contact with the enemy. 4 days later, they escorted bombers to Amiens. On December 11th to Emden. On December 13th to Kiel. 480 miles into German airspace. For the first time in the European Air War, heavy bombers flying daylight missions had single-engine fighter escort the whole way. The 8th Air Force in 1943 had been bleeding. In October of that year, the month that included Black Thursday, the second Schweinfurt raid, the 8th Air Force lost more than 9% of its bomber sorties. Of every 100 bombers that took off, 9 were not coming back. Another 45 would return damaged. On the single mission to Schweinfurt, on October 14, 1943, 60 B-17s went down. The crews called it the worst day of the war. The P-51B changed that equation in a matter of weeks. Between December of 1943 and February of 1944, the Mustang's escort range extended by two 108-gallon external drop tanks, pushed from 480 miles into Germany to well over 700. And then in January of 1944, General James Doolittle took command of the 8th Air Force, and he issued an order that changed American fighter doctrine overnight. Before Doolittle, American fighters had been ordered to stick close to the bombers, to fly as a defensive screen, to wait for the Luftwaffe to come to them. Doolittle released them. His new order was blunt. The fighters' mission was no longer to protect the bombers. It was to find the Luftwaffe, wherever it was, and destroy it. The bomber crews were furious. They had watched Mustangs peel off and disappear from their formations, and they felt abandoned. Some of them stayed furious for the rest of their lives. Some of them wrote memoirs 30 and 40 years later, still angry about it. But Doolittle had done the mathematics. The war in the air was not going to be won by defending bombers one mission at a time. It was going to be won by killing German pilots faster than Germany could train new ones. On January 11, 1944, a lieutenant colonel named James Howard, 30 years old, a former Flying Tiger who had flown P-40s in China, was escorting B-17 on a deep penetration raid near Oschersleben in central Germany. Howard became separated from his wingman and his squadron. He found himself alone above a bomber formation, with more than 30 German fighters in the area pressing home attacks against the fortresses below him. For the next 30 minutes, James Howard did not run. The bomber crews below watched a single silver fighter engage the Luftwaffe alone over Oschersleben. He shot down 3, damaged the 4th, broke up successive attacks on the bomber formation. When the B-17 crews landed back in England, they described what they had seen. James Howard became the only fighter pilot in the European theater of operations to receive the Medal of Honor. 1 month later, during what the Air Force called Big Week Operation Argument, February 20th through 25th, 1944, the 8th Air Force threw everything it had at the German fighter industry. Bombers hit aircraft factories across central and southern Germany. Mustangs escorted them the whole way. According to figures compiled at the National World War II Museum, Mustang pilots destroyed a significant portion of the Luftwaffe's most experienced fighter pilots during those 6 days. These are American claims. German loss records tell a slightly different story. But even in the German records, the Luftwaffe pilot corps came out of Big Week broken in a way it would never recover from. On March 4, 1944, the 4th Fighter Group based at Debden in Essex flew the first attempted P-51 escort mission to Berlin itself. Weather forced most of the bombers to turn back that day. 2 days later, on March 6th, the mission went through. 69 bombers were lost, the highest single-day loss the 8th Air Force would ever suffer over Germany. But the escort held. And the Luftwaffe had, for the first time, been forced to fight American fighters over its own capital. 1,100 miles round trip, at 30,000 feet, with fighter escort the entire way. The 4th Fighter Group was commanded by Colonel Don Blakesley, 26 years old, a former Eagle squadron pilot who had joined the Royal Air Force before America entered the war. He led from the front. Every major escort mission, every deep penetration, Berlin, Munich, Nuremberg. And then there was George Preddy, born in Greensboro, North Carolina. Slight of build, quiet, methodical. His squadron commander in the 487th Fighter Squadron of the 352nd Fighter Group was John C. Meyer, who would later become a 4-star Air Force general. Meyer said of Preddy, in remarks preserved in the 352nd Fighter Group records, that George Preddy was the greatest fighter pilot who ever squinted through a gun sight. The complete fighter pilot. On August 6, 1944, Preddy was escorting bombers to the Hamburg area. He spotted more than 30 Bf-109s forming up to attack a box of B-17s. He led his flight into the formation. He shot down 6 of them, in one mission, a record for a single pilot in a single engagement that stood through the rest of the war. Preddy finished the war as the highest-scoring Mustang ace, with a final official tally of 26.83 aerial victories according to the records of the United States Air Force Historical Research Agency. Preddy flew with the 487th under Meyer through the summer of 1944. In October, he took command of the 328th Fighter Squadron. He was leading that squadron when he was killed. He did not live to see the end of the war. On Christmas Day 1944, Preddy was leading 2 other Mustangs at treetop level in pursuit of a Focke-Wulf 190 near Liège in Belgium. He was chasing that 190 through an area that had been cleared for his low-level pursuit. Fighter Control had issued the standard ceasefire order to the American anti-aircraft units in the area. Any friendly aircraft below a certain altitude was to be presumed friendly, guns cold. But somewhere in the chain that order had not reached everyone. An American Quad 50 anti-aircraft crew defending the recently liberated town from the German counter-offensive that had begun 10 days earlier had not received the signal. They saw a fighter come screaming across their position at low altitude, and they opened fire. All 3 Mustangs were hit. George Preddy was killed. He was 25 years old. The Battle of the Bulge, which had begun on December 16th, was still going on. In the chaos of that offensive, communication between American units was breaking down constantly. Preddy died not because of the Luftwaffe, not because of the airplane, not because he had made a mistake. He died because a message about a Mustang chasing a Focke-Wulf at treetop level had not reached a gun crew that was frightened cold and looking at every fast-moving aircraft as a possible German. By May of 1945, when the German surrender was signed, the P-51 groups of the 8th, 9th and 15th Air Forces had claimed approximately 4,950 German aircraft shot down in air-to-air combat, and another 4,131 destroyed on the ground. These are American claims. Historians who have cross-referenced these numbers against German loss records, maintained by researchers like Jochen Prien and Werner Girbig, find, as they always find with air combat claims, that the real German losses were lower than the claims. But the direction of the war in the air is not in dispute. The Luftwaffe had not been outproduced. German fighter production actually peaked in 1944 despite the bombing. The Luftwaffe had been killed in the air pilot by pilot until the replacement pilots, being rushed to the front, were so inexperienced that the kill ratio became a slaughter. Göring, in his 1945 interrogation, was blunt about what he had seen happen. Long-range fighter escort, he told his American interrogators, had been the decisive factor. He had not believed it was possible. He had said so publicly. And now he was a prisoner. The Air Force he had built from nothing was gone. When he saw Mustangs over Berlin, he told them he knew the jig was up. But Göring still did not understand why it had happened. He still did not understand that the airplane that had destroyed his Air Force had been built on 3 engineering choices that every conventional analyst in 1940 had called mistakes. A radiator that produced thrust instead of drag. An engine that was wrong for its airplane until someone thought to put the right engine into the same airframe. A wing that failed at one thing and succeeded at another thing the designers had not even known they were trying to do. 3 mistakes that were not mistakes. Approximately 15,586 Mustangs were built, at a unit cost of about $50,000 each, cheaper than a P-47 Thunderbolt, a fraction of what a B-17 cost. The 8th Air Force's bomber loss rate, which had been over 9% in October of 1943, fell below 5% by the spring of 1944, and continued to fall as the Luftwaffe's ability to intercept eroded. Frederick Meredith, The British engineer whose 1935 paper made all of it possible never received any particular public recognition. He died in 1968. Almost no one in the aviation world, at the time of his death, fully acknowledged what his one obscure technical report had done. Edgar Schmued continued designing airplanes at North American. He led the design team for the F-86 Sabre, the fighter that would battle Soviet MiGs over Korea. He died in 1985. Ronald Harker, the Rolls-Royce test pilot whose 30-minute flight at Duxford had set the entire Merlin conversion in motion, died in 1999. George Preddy is buried at Green Hill Cemetery in Greensboro, North Carolina, next to his brother Bill, who was also killed flying a Mustang in April of 1945. Bill Preddy was 24. James Howard died in 1995. Don Blakesley died in 2008. Bob Chilton died in 2003. The airplanes they flew are museum pieces now. Airshow warbirds, photographs in books. The men who flew them are almost all gone. But the idea that built the airplane, the idea that a system designed as a whole could beat a set of components no matter how good each component was on its own. That idea is not a museum piece. That idea is the single most important lesson of the Second World War in the air. The side that thought about airplanes as systems won. The side that thought about airplanes as engines with wings around them lost. When Goering looked up at the sky over Berlin on that March morning in 1944 and saw silver fighters escorting bombers over his own capital, he thought he was looking at an airplane. He was actually looking at an idea that was 12 years old, written down in a dry British technical paper in 1935. Built into an American airframe in 102 days in 1940, and perfected by a British test pilot's 30-minute flight in 1942. 3 engineering mistakes, 1 airplane, the end of the Luftwaffe. War is mathematics, but the men who figured out the mathematics were not numbers, they had names, and they deserve to be remembered.